Welcome to episode 7 of the Semiconductor Age. In our previous episode, we explored why computers need memory. Now we'll go inside the memory chip itself and discover how microscopic semiconductor devices store, read, and preserve billions of bits of information. A modern memory chip may contain billions of tiny memory cells. Each cell stores information as a digital state, represented by a 0 or 1. These cells are arranged into highly organized structures, allowing enormous amounts of information to fit inside a remarkably small piece of silicon. At the heart of semiconductor memory is the memory cell. Its job is simple: store one bit of information and allow that bit to be accessed when needed. Different memory technologies achieve this in different ways, using transistors, capacitors, or specially designed structures to represent a stored state. Billions of individual cells cannot be controlled randomly. They are organized into rows and columns, forming a memory array. Word lines select rows, while bit lines carry information to and from the cells. This carefully designed architecture allows computers to locate and access specific data extremely quickly. SRAM, or static random access memory, uses several transistors to store each bit in a stable state. It is extremely fast and does not need periodic refresh while powered. However, it requires more transistors per bit, making it larger and more expensive. That's why SRAM is mainly used where speed matters most, such as CPU caches. DRAM takes a different approach. Each cell uses a transistor and a tiny capacitor to store electrical charge. A charged capacitor can represent one state, while a discharged capacitor represents another. DRAM offers high density at relatively low cost, making it the main working memory in computers and many other digital systems. SRAM and DRAM demonstrate an important engineering trade-off. SRAM is faster but requires more space and costs more per bit. DRAM is slower but far denser and more economical. Neither is universally better. Engineers choose between them depending on the required balance of speed, capacity, power, and cost. ROM, or read-only memory, is designed to preserve information without continuous power. It is commonly associated with firmware and instructions that a device needs to start or operate. Although modern systems often use programmable forms of non-volatile memory, the fundamental idea remains the same: essential information survives when the power is removed. Flash memory stores information by trapping electrical charge inside specially designed transistors. Because the charge remains trapped even after power is removed, flash is non-volatile. Its high density and low power requirements make it ideal for SSDs, USB drives, smartphones, memory cards, and many other portable devices. Flash memory mainly comes in two architectures, NAND and NOR. NAND connects cells efficiently for high-density storage, making it ideal for SSDs and memory cards. NOR provides faster random access to individual locations and is widely used for firmware and code storage. The architecture determines what each technology does best. Semiconductor memory performs three fundamental operations: read, write, and erase. Reading detects the stored state. Writing changes that state, while erasing removes previously stored information. The exact physical process differs between memory technologies, but these three operations form the foundation of digital data storage. DRAM stores information as electrical charge, but that charge slowly leaks away. Without intervention, the stored data would eventually disappear. Memory controllers therefore refresh DRAM cells repeatedly, restoring their charge before it becomes too weak. This refresh process allows DRAM to remain reliable while operating at high density. A single memory cell stores just one bit. Billions of cells become arrays, multiple arrays form memory chips, and those chips are assembled into packages and storage devices. An SSD combines many flash chips with controllers and firmware, transforming microscopic memory cells into terabytes of high-speed digital storage. There is no perfect memory technology. Engineers must balance speed, density, power consumption, cost, and endurance. Improving one property often affects another. The challenge is therefore not simply to make memory faster or smaller, but to find the right combination of properties for each application. At Physical Sciences Consultorium, we see semiconductor memory as more than data storage. It is an example of how physics, materials science, electronics, and engineering come together to create technology at an extraordinary scale. Understanding these tiny devices helps us understand the foundations of our digital world. In this episode, we went inside semiconductor memory, from individual cells to complete SSDs. But memory technology is evolving rapidly. In episode 8, we'll explore the future of memory, including 3D NAND, HBM, ROM, ReRAM, and other emerging technologies. If you found this episode useful, like, share, and subscribe to Physical Sciences Consultorium. Until next time, keep exploring, keep questioning, and keep discovering.